equation. See if you can make some headway on it. First one done, raise your hand so we can start as a group. It's not a race, but if you win, you get a prize.
Oh, man.
You don't have to take the final?
Jessica will share a snack with you.
No.
You better be first. There's this pile of snacks over here. Whoa. What grade are you in? 6th grade. My son's in 6th grade. I wasn't about to pull him out of school. It's too annoying. Is she even on the annoying spectrum? Oh.
Ooh.
Those tweens. Yeah. Yes. So, if the log and the exponential have the same base, then everything undoes itself until you get just the exponent. So the property, I'll put the property up here.
You still have to distribute the ones.
So if you have log base 5 of 5 to the x, that would just be x, if you had something like that. If. First step, collect logs. And now we can use a log property. We have two logs, same base, coefficients of 1, so we can mush them together. Log base 5 of, we'll distribute the x, so we get x squared plus 4x equals 1. Everyone good to that point? Now we use the definition of the log. Now we're going to move from a log equation to an exponential equation. And that's what the definition of the log does. The definition of the log allows us to go back and forth between the two. And the definition of the log, in terms of the exponential, says the argument is equal to the base raised to the other side. The other side is a 1, so we just get 5 to the 1. Not too big a deal. So we have x squared plus 4x minus 5 is 0. One thing that we have to have in our mind, though, right here, we should have a little bell going off in our head. That was a log property, and as soon as you trigger a log property, you might have introduced an extraneous solution. As soon as you use a log property, be aware. Whoops, I think I factored it wrong. That should be a plus, and this should be a minus. So this tells us that x is negative 5 or 1. And then here we have to check. We started with a log equation. We used the log property. That could be trouble. And the check is cursory. We just go back and make sure that we're not taking the log of something that's non-positive. And oops, we are. Here we're taking the log of a negative. Here we're taking the log of a negative. So bad. So this one gets knocked out. When we plug in 1, log of a positive, good. So the only solution there is 1. All right, one solution only. Here is an exponential equation. since the bases can't be made to be the same, we have to ln it. Take the natural log of both sides. So that's your hint. So go ahead and see if you can ln it successfully. ln it. ln it.
What do you mean double?
Log both sides. Once we take the natural log of both sides, then we definitely are going to be jumping right into log properties. So in your mind, remember, log properties were used, so we might have extraneous solutions. On the left, that one's pretty easy. How about on the right? What's the predominant operation inside that log argument? Multiplication is the predominant operation, so we turn it into addition. So this becomes natural log of 64 plus natural log of 3 to the x. On the left, let's distribute. Our end goal is to get all terms with an x to the left. Our end goal is to get all terms with an x to the left. And it looks like we have two terms with an x, two terms without an x. So we'll move those guys left that have an x. On the left, we factor the x out. On the right, is there anything we could do?
The natural log of 64 could be natural log, or it could be 3 natural log of 4.
You just multiply.
Over here?
Yeah.
Yep, you could combine those in a number of ways. Because it's addition, you could say that's 4 times 64. Or I think you were suggesting that 64 is 4 raised to the 3 power. So you could combine them that way too. Yep, several ways you could do it. And then our last step here, that's going to be turned into natural log of 4/3, so we would end up having to divide both sides by natural log of 4/3. And once we have a log divided by a log, you can't mush those together in any way. A log divided by a log. So that is our exact answer. What's that?
Why did you use the
not that one, the next one. What did you do?
Here,
To get there.
to combine these two.
No, from the one above it.
Here?
Yeah.
So here to here is a grouping step. This has no x in it, so it stays to the right. This has no x in it, so it also goes to the right. So it's the two that have no variable, so they're just constant. The constants are going to the right, and the variables are going to the left. And then factor the variable.
For the final, do you generally choose for the first 3 exams, like the most difficult 3 off the first 3 exams, or is it randomized?
It's pretty random. I mean, there's ones that are more important than others for sure. There's some, like if we look at exam 1, and it's a lot of questions, 15 questions, and I'm only picking 3.
Yeah.
So, the true-false one, I'm probably not going to pick that. Draw a unit circle, I'm not going to pick that.
That's important.
That's an important one.
It is important.
Now, graphing on the first test, there was 4 graphs. Definitely going to pick a graph, because that's an important thing, being able to graph your trig functions. So I'll definitely pick, one of the 3 will definitely be a graph. And another thing is evaluating trig functions is so important. So, like, 6 and 7, those are pretty important types of ones, where you're given some information and you have to find all 6 trig functions. So, I certainly would say you should be studying everything, but there's some that you can kind of eliminate based on common sense.
I have a quick question.
Yeah.
Are you taking the exact problem, like word for word, number for number, or is it going to be like the same type?
I'm going to take the exact problem, but then change the numbers.
Okay.
Yeah, so the wording will be the same. What you're looking for will be the same. So, for example, if I took over number 6, the only information there is -5, 2. I would just change the point.
Okay.
Yeah. So I think with some deductive reasoning, you can eliminate 2, 3, or 4 from each test. But definitely, graphing was a big part. So one of the 3 is definitely a graphing problem. Definitely a graphing problem. All right, let's take a couple of questions from exam 1. Nice segue. Or the new technology, nice one wheel. Have you guys seen the one wheels? Those things are crazy. They're only $1,500 so far.
Oh my lord. I bought a car for half that price.
I know. How many wheels did it have?
4.
Imagine paying more for one wheel. But you can't go on mountain bike trails, can you?
I could, it's just biased.
Yeah, I saw my first one last weekend in person. It's like, woo, wow, those are cool. All right, so this is a good type of question to make sure you're clear on in exam 1. Common type of question, finding the trig function values given a point on the terminal ray. So it says find the exact trig function values. And let's see how you do it. So I'll just plot the point first and then tell us where to go. Okay, so our goal is to find the trig function values with that information. Trig function values. So this is a particular question. You can draw your theta however you want. It just has to have this terminal ray. You could think of it that way. You could think of it counterclockwise. It doesn't really matter. But we want to know the 6 trig function values for theta given 2 -3's on its terminal ray. What's the first step? find r. Yeah, we called it r back in these days. That's r. So we use the Pythagorean theorem. R squared is 2 squared plus negative 3 squared. Make sure you're wrapping things up. Don't be losing a minus sign. So we see that r is root 13. So we square the entire coordinate, including the minus. And then we have to be familiar with our ratios. And so we've got all three quantities. We've got x, y, and r. So x, y, and r. And those three things get combined in 6 different ways. We just have to remember the order. So sine is going to be what? Y over r, so negative 3 over root 13. And here, again, I don't care in a case like that if you rationalize or not. It doesn't matter to me. And how about cosine of theta? X over r, so that's going to be 2 over root 13. Tangent? Y over x, negative 3 halves. So those are our primary three. And then as long as you've written your table the same way you should always write it, we just have to take the reciprocals in the right place. So here we'll get negative root 13 over 3. Here we'll get root 13 over 2. And here we'll get negative 2/3. Let's do a graph. Okay. Factor first. So let's remember that the angle has to be factored before we go anywhere. So inside we have an x over 2, so we're going to factor out that 1/2 so that we have an x minus or plus something. And what is the second term inside the parentheses? False. 4 pi. So we're factoring 1/2 out. So when you pull 1/2 out of an integer, that integer's place increases. Right? If you factor half out of 4, you get 8, because there's 8 halves in 4. So if we're factoring out a fraction, we should be left with something that's larger. So a half pulled out of 2 leaves 4. And you can always double check by distribution. Half distributes to the x, giving half x. Half distributes to the 4, giving 4 pi. Half distributes to the 4 pi, giving 2 pi. Good? So then, once it's factored, we are dealing with a function that's a reciprocal function. And reciprocal functions, namely cosecant and secant, those are the two reciprocal functions that we do what I'm about to do with. We have to graph those two reciprocal functions using a guide function. So we generate our guide function. Usually I just call that y. And the guide function is the reciprocal. So the reciprocal of cosecant, the reciprocal of secant is cosine. So I just replace with the reciprocal function. So there's our guide. And now we're going to identify properties for the guide function. So we start out with the guide by looking across from left to right. Is there a reflection? Does this guide have a reflection?
Yes.
Yeah, there's a leading minus, so there is a reflection. And then we figure out the amplitude. What would the amplitude of the guide be? 2. Amplitude, remember, is the absolute value of the leading coefficient. So it's all the way on the outside. It's the absolute value of the leading coefficient. So amplitude is positive 2. Period. So we go to the basic period for cosine. And for sine and cosine both, that basic period is 2 pi. Right. That thing in there is a horizontal adjuster. That's a period adjuster. And since it's less than 1, it should be stretching the period. Right? And so we take the basic period, which is 2 pi, and divide it by that period adjuster. And that will give us the transformed period, which will be 4 pi. But now that we've done all the algebra and it's a little more fresh, you can sort of remember in your head that, oh yeah, if there's a fractional multiplier on the inside, that's a horizontal stretch. So the period of the transformation should be bigger than the period of the basic. Phase shift. Another word for horizontal shift, which you can only see properly after you have factored the angle. So what's that phase shift? Yeah, 4 pi. It's going to go right 4 pi. And then the vertical shift is exactly what we see out there, plus 1. So that's up 1. All right, so those are the properties of the guide that we'll use to graph the guide function. So we're told that the phase shift is 4 pi, so that's where we start. And we always start at the phase shift. So 4 pi, that's the left end point of period 1. 4 pi, left end point, first period. We need to figure out the right end point of the first period. And how do we get to the right end point of the first period? Add 4 pi to it? Is that what we said? So we're starting at 4 pi. The period tells us the distance from the left end point to the right end point. So if we know the left end point's at, if we know the left end point is at 4 pi, and the period is 4 pi, that tells us that the right end point's at 8 pi. So that's the second step. Add the period to the phase shift. Okay, so now we want to draw our center line. And our center line, we need to know how far above or below the x-axis we go. And the vertical shift is 1. So the center line is going to be between 4 pi and 8 pi at 1 unit up. So that's our center line. The amplitude will tell us how far above and below that to go. So the vertical shift tells us how far above or below the x-axis the center of the graph will be. Now, look for the amplitude. And the amplitude tells us how far above or below the center line to go. So amplitude is 2, so we need to go 2 above it, and we need to go 2 below it. And off on the side, let's get our shape for our guide. So cosine normally starts up, comes down. This is the shape for cosine. Not shape for minus cosine. This is the shape for cosine. The reflection obviously is going to come into play, but that's our basic shape for a cosine first period. So now we take our shape, we take our reflection, and graph it. So normally, if we had a cosine that wasn't reflected, these 2 points would be up. But because of the reflection, those 2 points are down. So we put those 2 points on the graph. The center points aren't going to matter. The points that are right on the center line, they're not going to matter that there was a reflection. They'll still be in the same place. And instead of 1 point in the middle down, we have 1 point in the middle up. So that will be our guide function. Asymptotes. Wherever the guide crosses the center line, there is an asymptote. So let's drop those guys in. So there should be an asymptote there and an asymptote here. Now we have to just draw the pieces. Draw the pieces. So there is a piece here, opening down. There is a piece here, opening down, approaching those vertical asymptotes. And then there is a piece opening up, approaching both those vertical asymptotes. Looking a lot like a parabola, but it's not. Parabola would spread out wide infinitely. This does not. Nice and contained. So there's our graph. First period of the transformation. We will be asked to identify the domain and the range. So the domain. What's the first part of the domain? Negative infinity to what? Because this graph repeats itself again and again and again and again and again. So we think first about the domain. It wants to be all reals, except those asymptotes are bad points. So in our mind, when we think about the domain, we should be thinking all reals except the asymptotes. So we don't want to go negative infinity to negative 4. We want to be thinking all reals except asymptotes. So that's how we'll write this. We'll say it's all reals except x is not allowed to be an asymptote. So we just need to figure out an asymptote and the distance between consecutive asymptotes. It doesn't really matter which asymptote you start with. You could start backing up here. But it's important to realize that there is 2 pi between consecutive asymptotes. So it's totally fine if you want to say your first asymptote is 5 pi. Totally fine. You don't have to come back over here and start figuring them out and say, oh, well, there's an asymptote and there's an asymptote. Doesn't matter. You can. But it's just perfectly fine to say that the first one that we see with our first period is at 5 pi. So the 5 pi goes there. It's not equal to be 5 pi plus 2 pi k. Since 2 pi is the distance between consecutives. Now at the range, we do an interval thing like you were suggesting. So we start at negative infinity, coming up the y-axis, and then we have to stop at negative 1. We include negative 1. No points in the range in here, but then we pick up again at 3. So for the range, we get that interval. All right, so when you look at that, any steps, factoring, very, very important. If you don't factor right, then you're messed up all the way through. Basic period for sine and cosine 2 pi. Is that okay? What's the basic period for tan and cotan? Pi. Do you use a guide function when graphing cotan? No. The only two you use a guide for, cosecant and secant.
Or cotangent is basically you just reflect the graphs of the tangent, right?
You can think of cotangent as a reflected tangent. That's the shape of it, but then the endpoints are a little different. For tangent, the endpoints are 0 and pi, but for cotan, the endpoints, oh, I just said that backwards. For tangent, the endpoints are minus pi over 2 and pi over 2, but for cotan, the endpoints are 0 and pi. We can do one.
Should we review odd-even functions?
Odd-even is very helpful me think about that. We did have a graph that used that. I would say yes.
It's on our formula sheet, isn't it?
Yeah, it is. I would say yes, because it's only helpful if you have a trig function that has that leading minus. It's just nice to know whether you can get away without knowing it. You can do a horizontal reflection instead of knowing that it just erases. But if you know that it erases, it's a lot easier if you know those. Which are the only two even functions? Cosine and secant. The other four are all odd. So with, let's see what I had there. Let's do this. So if your function looked like sine of minus 2x plus pi, what would we do here? Well, no matter what, you would first factor out the negative 2. You already know that you have to factor out the leading coefficient. All right, so that would be your first step. And then, if you wanted, you could say, hey, that's a horizontal reflection, and just go with it. That's fine. But if you know your odd-even properties, you can say to yourself, oh, sine is an odd function. And so what's true about odd functions? How do odd functions, how is that leading minus affected by an odd function? It jumps to the front. So that jumps to the front, leaving you this. So that's because sine is odd. And the only even functions are secant and cosine. So if we had something like this, if we had cosine of negative 4x minus 2 pi, something like that, same start point, you have to factor the angle. So you get your angle factored. And then because cosine is even, what happens to the minus? Just vanishes. So that's because it's even. So I think knowing them definitely helps. You know, you're good at doing horizontal reflections now after we've done some with algebra, but let's just simplify it a little bit. And recall that our basic principle for odd even for trig functions is really kind of convenient, and I think that it's easy to remember. If you think about the unit circle, we define, if we say that this is theta over here, this positive angle, then the coordinates are cosine theta, sine theta, if this is a unit circle. And if this is minus theta down here, then this is cosine of minus theta, comma sine of minus theta. And what we see is that cosine theta and cosine minus theta, they're the same. All right, everyone agree? Those two are equal. So cosine of minus theta equals cosine of theta. And if we look at sine of theta and sine of minus theta, there's sine of theta, and there's sine of minus theta. We see that sine of minus theta is the same magnitude as sine theta, but there's a minus out in front because it's going down instead of up. So that's the picture in your mind that helps you remember that cosine is even because cosine of minus theta and cosine of theta have the same exact x value. And sine is odd because you have to go down instead of up. Any questions on the odd-even piece? let's see what I have there. Let's do one more of these graphing type ones just to make sure we get it. So let's graph f of x equals -2 cotangent of x plus pi over 2 minus 1. So do that one.
I can't remember, should we still use a guide?
No guide.
On a tangent.
No guide. No guide on tan or cotan. The only two that we ever use a guide for is cosecant and secant. Cosecant and secant are the only guides. So we do a direct approach for the other four. Direct.
My amplitude is not available.
Yeah, not applicable for tan or cotan.
It's been a while.
I know. Tangent is the one oddball. Tangent is where the phase shift is the beginning. Oh, yeah, excuse me. Whereas the middle. Tangent is where the phase shift is the middle. Cotangent, you do it just like the others. So properties, is there a reflection? Yeah, definitely. How about amplitude? Yeah, amplitude doesn't matter. It affects the steepness of the graph, but it doesn't come into play for us when we're doing our graph. So amplitude by definition is the maximum distance above the center of the graph, and there is no maximum distance. So that coefficient can affect steepness, but it's not an amplitude. Period. So basic period for tan or cotan is pi. if there was a multiplier of the angle other than 1, it would adjust the period. Pi divided by that number, exactly. So if that number was a fraction, say 1/3, we'd end up with a period of 3 pi, which makes sense because if that was 1/3, that'd be a horizontal stretch. Stretch it out to 3 pi. Phase shift, left pi over 2 and down 1. Okay, so here's where we have to be careful. After you get into the habit of graphing tangent, you have a habit that should not be applied to cotangent. With tangent, we found our phase shift, and then we took our first period and we used the phase shift as a midpoint. Tangent's the only one that's different. So for cotangent, we use the same old stuff. Phase shift is the left endpoint. So phase shift here is minus pi over 2. So we go to minus pi over 2. That is the left endpoint where there is an asymptote. So at negative pi over 2. Just like sine and cosine, we take the period, add it to the phase shift, and that gives us our next point. And that's pi units over here, so that would be at pi over 2, right? And that will be our other asymptote, our next consecutive asymptote. Our vertical shift is minus 1. That is going to be the only key point that we really need. The shape of a cotangent is down to the right. So that's what we would have down to the right if there was no reflection. But because there's a reflection, it's actually going to look more like a tangent, and it's going to go up to the right. So it'll look like that. And then we have to figure out our domain and range. So any questions up to that moment? Domain for this function? Like any trig function, it wants to be all reals. But unless you're sine or cosine, not all reals. Got to throw out the asymptotes. They don't belong. So what's the first asymptote? Yeah, so x cannot be pi over 2 plus the distance between consecutive asymptotes is whatever the period is. Do that. An easiest question on the test. The range of a tan or a cotan, all reals. Let's do a tangent one right next to it just to compare how they're different. So let's graph f of x equals 4 tangent of 2x minus pi over 2 minus 3. Factor out the 2 properly. Double check that you know how to factor out 2. Hopefully you factored it right. I put the right factorization up there. Should be factor ninjas by now. All right, let's go through these properties as a reflection. Yeah, no reflection. Amplitude, NA. Period, pi over 2. So basic period for tan or cotan is pi. This is a transformation, so it's got to have an adjusted period. We divide the basic period by 2, thinking in our head, coefficient bigger than 1 on the inside is a horizontal compression. That's what it's done. It's compressed the period from pi to pi halves. Phase shift,
Right.
opposite of what we see. Vertical shift, exactly what we see. Okay, so here is the funny part. Okay, so the phase shift is at pi over 4. So, I'm going to subdivide this. That's pi over 4. That's pi over 2. That's minus pi over 4. And minus pi over 2. Okay, phase shift is pi over 2. Excuse me, pi over 4. So what do we do with that pi over 4?
That's your middle.
That's going to be the center of the first period. So that's not an endpoint. So pi over 4 is the center. So that's going to be the center of the first period, not the left endpoint. Then we take our period, which is pi over 2, and we need to position it so that pi over 4 is the midpoint of that interval. So we take an interval that's pi over 2 radians long, and we're going to squash it on there, and that will be where we want to go. And it's pretty obvious, I think, that that period is going to be sitting from 0 to pi over 2. If we take an interval pi over 2 radians long, and have pi over 4 as the midpoint, that's what it'll look like. Everybody okay with that? And then our vertical shift is 3. So that allows us to put our center line right there. So from 0 to pi over 2 is the period. Center line down at -3. And let's plop our shape over here. The shape for an untransformed tangent looks like that. And that's what the shape of our graph will look like as long as there's no reflection. Okay, we don't have a reflection. So that is what our shape will look like. Our key point is right here. So from that key point, we're going to go up, right, and down, left. Go up, right, and down, left. And that asymptote will not be crossed, ever. So that'll be our first period of the transformation. You're bringing me back. Domain and range. The domain of any trig function wants to be all reals, but you gotta throw your asymptotes out. So it wants to be L reals, but those pesky asymptotes have to be thrown away. Where's our first asymptote?
0.
Yeah, right at 0, or we could say pi over 2, either one. So what's our pi over 2k, our form?
Would you mark it wrong? Price is 0 plus pi over 2k.
No. I won't mark that wrong. There's other stuff that you probably will do that will mark wrong, but not that. I won't mark that one wrong. Yeah, totally fine. Totally fine. All right, any questions on that graph? So those are the two that you really should compare. Make sure you have the difference between cotan and tan. That's where a common mistake occurs. All right, let's do a couple more. So from exam 2, suppose the tangent's -4 and theta's in quadrant 4. Find the exact values for these double angle expressions. First thing in your mind, definitely draw a picture. How you want to do it's totally up to you. I guess let's do it this way. We know we're in quadrant 4, and tangent is basically slope. And so we know right off the bat that we've got a pretty steep line here. Tangent of theta is -4. So we're dealing with something like that. What would be good coordinates to put on that point down in quadrant 4 that would generate a line with a slope of -4? 1, -4. Yeah, that's the natural choice. That's what I would use. 1, -4. Everyone agree that if we have a line through the origin with that point on it, slope's -4? Y over x. How about the r value? How do we find that?
1 squared minus 4 squared plus r squared.
So r squared will be 1 squared plus the quantity -4 squared. Again, don't forget that coordinate is wrapped up. So your r value is the square root of 17. And it's positive. That's the distance to the origin. Okay. So now this is giving us a lot of information about angle theta. This is telling us that sine of theta is equal to -4 over root 17. This is telling us that cosine of theta is equal to 1 over square root of 17. Okay, but that's not telling us anything directly about the trig function values at 2 theta. Right? At 2 theta. So how are we going to get in here?
Sine squared plus cosine.
Nope. Yep. So the double angle identity for sine of 2 theta is 2 sine theta cosine theta. So we know the value of the sine function for 2 theta by finding the sine value for 1 theta and the cosine value for 1 theta and then multiplying according to that formula. Okay, so we have information on the right about sine and cosine of 1 theta. And we use that to find out information about 2 theta. So this tells us then that we multiply 2 times -4 over root 17 times 1 over square root 17 So that will be negative 8 over 17. So that is the sine value for double theta. Cosine value for double theta. Exactly. So our formula is cosine squared of theta minus sine squared of theta. So we take cosine of single theta and square it. That's 1/17 minus we take sine value of single theta and square it. That's 16/17. And our conclusion is that, oh, that's far away. I know, I'm going to need one of those. Oh, got it. Holy cow. That would be our cosine value. And then tangent is found by using those two. Don't need to have a formula for tangent. For tangent, we're just going to go with the flow. We know that tangent of 2 theta is sine 2 theta over cosine 2 theta. So we'll go with the flow. We've got minus 8/17 for sine of 2 theta. We're going to flip the cosine of 2 theta value since we're dividing by a fraction. We get quite a bit of cancellation here. And we end up with 8/15 for the tangent value.
Yeah, you can use the numerator, so we get the same thing.
Yep. So, question, what quadrant is 2 theta in?
3.
So we hear that 2 theta is an element of quadrant 3. Let's see, does that make sense? Sine and cosine of 2 theta are both negative, and tangent of 2 theta is positive. Those properties are all part of quadrant 3. Negative cosine, negative sine, positive tangent. So those are all part of quadrant 3. Yes.
So the formulas for the double angles are going to be
On that formula sheet, yes.
Where is that?
If you go to D2L and you go over to content and you look under exam information.
How long ago did you put that out?
What's that?
How long ago?
A couple days ago.
Oh, okay, yeah.
Monday or Tuesday.
Under
It's on your course doc.
Oh, I'm sorry. Course documents. It's the top item under course documents. Yeah, that's right. Course documents. Top item. All right, let's plow through these last two, and then we'll go do something else. I know what I'm going to do. Time to pop a pill.
Oh, man.
All right. 7 pi over 6. First off, let me ask you the question. Does inverse sine have values on the top or on the right? Inverse sine has values on the right. Is 7 pi over 6 on the right? No. So we can't just employ the freshman dream and erase those two things. Cannot do it. But what we can do is a little computation. Sine of 7 pi over 6. 7 pi over 6 over here on the 12-sector circle. Sine is the y value. It's the short leg. So sine of 7 pi over 6 is... Wow! It's either 1/2 or square root of 3 over 2. 12-sector circle. Half is shorter than root 3 over 2, so it should be the short leg, so 1/2. Yeah, I know what you guys are going to be doing after class. It's becoming clear. So now we say, what is the inverse sine of 1/2? We say, oh, it's an angle on the right that has a sine value of 1/2. And this is the angle on the right that has a sine value of 1/2. That angle is 5/6, correct. So that is where we're going. One more. We should be able to finish this pretty easily. Okay, so this one, we don't have anything super specific, like 7π/6. But what we know is that inverse sine is an angle on the right. So we just need to draw a picture that helps us with this. And it doesn't matter if we pick quadrant 1 or quadrant 4. We need to draw a dot that satisfies the condition. I'm going to put it in quadrant 4 because I have more space down here. And I just need a dot that has a sine value of t over t minus 1. So I'm going to call the hypotenuse t minus 1. I'm going to call that x. Do you agree there? The sine of that angle is t over t minus 1, right? Y value over the r value. Well, we don't know what that x is, so we have to find it. So x squared plus t squared will be t minus 1 squared. Okay, so that tells us that x squared is going to be, I'm going to FOIL this out. So x is going to be the positive square root. We're on the right side of the circle, so it's got to be a positive square root. X has to be a positive number. So we get that. And now the question says, what is secant of this angle? What is secant of this red angle? Secant of an angle is the reciprocal of cosine of an angle. Cosine of this angle is x over t minus 1. So our answer should be t minus 1 over x. That will be our answer. Beautiful. Yeah, so double check on that one. Make sure each of those steps make sense. And I'll see you all Tuesday. I'll see you in the final week. Woo, the final week. Good luck studying this weekend. Take advantage of it. None of that slack.